Hello. Hi everyone, welcome to Green Software Brighton, March edition. Yes, hello to everyone online that's watching as well. My name is Mark, I'm one of the 4 organisers of GSB, along with Ollie and Fiona and Adam, who's not here tonight, but he's got a very good excuse, so we'll let him off. So we're Green Software Brighton. We are a community here in the southeast of the UK, and we are curious about how digital technologies impact the environment. So we do a lot of different events, so we've got talks like we've got tonight, but we also run workshops, panel discussions, different things where you can come in and get involved and try and get people thinking about tech and the impacts on the environment and what we can do to reduce those. Our next event is in April, and it's going to be Adam Newman is coming to talk about, just going to get the title up, how to build confidence in your website's sustainability credentials. So if you are building websites and you want to know how sustainable they are or are interested in green hosting and that kind of stuff, then that's a talk for you. And that will be the 3rd Wednesday in April, whatever date that is. I'll do a little thank you to our sponsors. So tonight, Runway East are hosting us in Brighton, which is a great office space. They give us this space for free to run the event, so that's great. Thank you, Runway East. Root and Branch are a local software consultancy. They also do green web hosting, and they have bought the pizzas for us tonight for those in the room. So thank you to Root and Branch. Go and chat to them if you're interested in kind of web measurement technologies and green hosting and all that good stuff. We've also had drinks bought for us tonight by LTUX, which is another meetup group, and they are local to Brighton, do great stuff in the world of UX. And we actually ran a joint event with them last Friday, which was Green Software Practitioner Training. And the ticket money that we got from that, we've put back into our meetup groups, so they've paid for the drinks tonight, so thank you to them. We're also supported a bit by the Green Software Foundation, who do a lot of great work with standards and tooling and things in the green software space, so go and check them out. And Silicon Brighton are the awesome Brighton Tech meetup community. I'll hand over to Cam, who's going to talk about them a bit.
Thank you, Mark, and a special thanks to Ollie. Cheers. Hey, everyone, my name's Cam. I work for Silicon Brighton, and as the slide says, we are the hosts of Brighton and Hove's digital tech sector, more than just tech sector. But yeah, we look after a load of different meetups here in Brighton and Hove. Loads of groups here. Sorry, Word Up, for that horrible block there, but you should go to Word Up. But yeah, a lot of our meetup community hosts all jump in and help out each other's communities, like Learning Future, Green Software, and LTUX, to sort of name but a few. It's a brilliant community of communities. So if you're enjoying this evening or have enjoyed any other Silicon Brighton events, I urge you to go to the other Silicon Brighton events. We ourselves are supported by loads of supporters, all local companies that see value in community. So they support us, whether that is, to be honest, that all of our live streaming is supported by our supporters. So that helps us beam out to the whole world. So we're massively appreciative of that as well. A huge thank you specifically to our sponsors as well, who are yearly recurrent supporters who sponsor us, looking after us with Plus Accounting, More Law, Alirity, and James Chase. So huge shout out to them. You can stay up to date on all of our activities by this link just here. It's also the portal to our Slack channel as well, which is brilliant if you're looking for jobs or extra community events. They're all posted there, and it's brilliant. Like, you meet someone, you maybe get their name, catch it, type it in there, you'll find them easy peasy if you didn't happen to catch their contact details. We are also running our very own conference again this year. Last year we did it at the Dome. This year we're going bigger and better at the Brighton Centre. It's a brilliant day. We had loads of involvement from the Green Software crew last year, along with all of our other meetups. So again, if you've enjoyed a meetup and want to go see it on, hate to say on steroids, but you can come to a fantastic day on the 26th of June. You might hear conference ticket and think, gosh, that could be like £300 or so. We keep keep it a community discount. The standard price is £40, and that halves with the GSB discount to £20, and £10 of that goes right back to the Green Software crew, and they can use it for whatever they like. So if you've enjoyed a drink or a bit of pizza today, or a venue, then yeah, give a bit back to the community, whilst also getting to go to a great day out. I believe that's me. Most of the time it is. Oh, it's not working. Oh, that is me, because it's the last slide, isn't it?
Cheers, Cam. Yes, use the code GSB because we get money. Go for it. So yeah, tonight we've got the wonderful Charles Humble, who's going to come and talk to us about this thing. I don't know if any of you heard of it. It's called AI. It's this hot new thing that everyone's talking about. But yeah, so apparently it uses a lot of energy and it might not be that great for the environment. So yeah, please welcome Charles. He's going to come talk to us about that.
Thank you. Thank you very much. Right. Hurrah, it worked. Brilliant. So, 2 years ago now, about 2 years ago, a spokesman from Microsoft visited a special school near where I live in Surrey to give a talk to a group of autistic teenagers about AI and how wonderful it was going to be for all of their futures. And he started rather bravely by saying, "Do any of you know what AI is?" And one young man put his hand up and said, "Well, it's a failed attempt to simulate human intelligence using a Turing machine." And the guy from Microsoft looked at him and said, which was probably unwise, "What makes you think it's a failed attempt?" And the young man took a deep breath and said, "Well, for a start, artificial neurons are a gross oversimplification of how neurons actually work in the brain. But anyway, brains don't work like that. They're probably quantum devices. I mean, I'll admit the evidence for that is quite scant, but quantum biology is clearly an interesting field, and you should totally look into it. And you can, of course, simulate quantum devices in a Turing machine, but, you know, that's probably not what you're doing," and on and on and on and on. And after about 5 minutes, the Microsoft person concurred that it was indeed a failed attempt to simulate human intelligence with a Turing machine. And added rather charmingly, I thought, having spent 5 minutes talking to you, I'm not even sure I know why I'm so excited by it anymore. Failed attempt to simulate human intelligence with a Turing machine, though it may be, AI is having a bit of a moment, right? We're all under pressure. Whatever you do in this room, I imagine, you are all under pressure to be adopting generative AI into your working practices in some form. So I think it's quite helpful to take a bit of a step back, think about how we got here, and think about what the implications of what we're doing actually are. When you think about how software develops, it has historically tracked Moore's law fairly closely. So Moore's law is the observation from Gordon Moore in 1965, that essentially we double the number of transistors every 2 years, and we halve the cost of compute every 2 years. Right? It's not a law of physics, Moore's law. It's a law designed to extract money from venture capitalists, but it kind of does that job quite well. It was true for a long time. I mean, it's not really true anymore, but it was true for a long time. But the simple way to think about that is basically software tracks hardware. So as our hardware gets more capable, so our software gets more capable too. And AI is exactly the same deal. So if you think about the very beginnings of the field, I would probably date that to Alan Turing and the bomb, 1939, beginnings of the Second World War, essentially. That's probably where I would trace it to. You could arguably say it's Charles Babbage and Ada Lovelace a couple of hundred years earlier. The trouble with that is they couldn't actually build the stuff. So I would give it to Turing just about. But those are mechanical devices, right? They're physical machines, not software. And that's really where this idea of, can we build an artificial brain, that's where that idea starts from. I mean, if you trace what happens through the models of the 50s and 60s and 70s and 80s and 90s and so on, you get this kind of pattern like that, where we discover a new technique or we rediscover an old technique because the hardware suddenly allows us to do something we couldn't do before. And we get very excited about that, and lots of money pours into research. And then after a bit, we realize it was a terrible idea, and we sort of back away, and we go into this AI winter thing, right? And that's more or less been the pattern pretty much forever. That tells us a couple of things I think are really interesting. And one of the things I think it tells us that's really interesting is that there is something very appealing to us as human beings about having a machine that thinks like we do. Right? It's been a dream of people for a very, very long time to have such a thing, which is why when the breakthrough happens, we tend to get very excited by it. There's also some interesting things to do with particularly language models in that they break our heuristics. So we think they're much smarter than they are because we associate language with thought, even though language and thought, or thinking and language are two separate systems in the brain, probably. But we tend to think of machines that speak to us like humans as more smart than they actually are. The current breakthrough is the large transformer model. I've dated that to 2012. That's something called AlexNet. You could actually date it to 2017, which was the publication of the Attention is All You Need paper. It doesn't terribly matter. But basically what we're saying, the technique itself isn't new, by the way. The technique itself goes back to at least the 70s. But what's new is suddenly we're able to do it at scale. So another of these laws that aren't laws of physics, but laws to extract money out of venture capitalists is Sam Altman's AI scaling law. And basically he says, the bigger you make bigger and bigger models, and eventually you get to generalized intelligence and profit. Right? It's total nonsense, but gullible people believe it, and that's good. Or it is good if you're Sam Altman. So the way this works is you need a couple of things. You need a staggering amount of data, right? Ideally all the data. So if you're trying to make something that produces text as an output, what you need is vast corpus of text. If you want images, obviously vast corpus of images, music, vast amount of music, and so forth. We have the internet and also no ethics or morals, so that's good. So we can just take all of the internet and feed that into a training process. And then at the end of that training process, what we do is we use a bit of very basic behavioral learning, something called reinforcement learning with human feedback. We use that to tune the outputs that the large language model produces, and at the end of that, we have a machine that imitates things it's seen before, using stats and maths. Sorry, I write for American papers, and occasionally I forget who I am. It's terrible. Anyway, so that's essentially what these things are. A nice way to think about this is if you take a load of words and put them in a pot and sort of stir them around, what it will do is pick the words from the top. And that's really all this is. It's just stats. Doing that, as I said, requires an enormous amount of data. It also requires something else, which is a staggering amount of compute. And in fact, I got interested in this story originally because I saw this from the International Energy Agency, which says combined electricity use from Amazon, Microsoft, Google, and Meta had more than doubled between 2017 and 2021, rising to 72 terawatt hours in 2021. And I thought, that's very odd. I wonder why. Now, I wear a stupid number of hats professionally. I'm a consultant, but I'm also a tech journalist, and I'm a white bloke, so I have a podcast, and I do a whole load of things. But one of the things I am as a tech journalist, I thought that was odd. So why did I think it was odd? You might think this is obvious, right? You might think, well, hang on, we moved to a utility compute model. Utility in the broadly mapping sense, like electricity. We don't run our own data centers anymore. We rent them from Amazon or Google or Microsoft. So you'd think the answer to that might be obvious. You'd be wrong. It turns out Google and Microsoft and Amazon are very good at running data centers efficiently. And that's also where their profit margin is. So it's in their interests to bring the PUE numbers, basically the amount of waste there is in the data center, down as low as you can bring them down. So for quite a long time, even though we were adding a lot of compute into Amazon and Microsoft and Google, their actual electricity bill wasn't going up very much. It was barely noticeable for a long time. So I thought this was weird. So I asked people I knew at companies like Amazon and Microsoft and Google what on earth was going on. And when I did that, I noticed a really interesting thing, which is the person I was talking to looked awkward and tried to change the subject. That's a great sign as a journalist, because that tells me there's a story there and you don't want me to know what it is. And that's actually what journalism is. There's a famous quote often attributed to George Orwell, but probably wrongly, I have to say, but it's a good quote, which is that journalism is telling a story someone doesn't want you to tell, everything else is PR. It's a bit harsh, but I rather like it. So as I say, I got interested, I went digging. It took me a while, 2 years in fact. But it turns out that companies like Microsoft and Google do publish environmental reports. Those environmental reports are a bit hand-wavy in places, but occasionally they accidentally reveal something quite interesting. For example, Microsoft revealed in May of 2024 that its total carbon emissions had risen 30% since 2020. 2020 is the benchmark year that they use, the baseline year, primarily due to the construction of data centers to meet its push into AI. Okay, that's interesting. Google's emissions, meanwhile, have surged 50% compared to 2019 and 13% in 2023 alone. Again, that's according to their own reporting. Again, that's because of AI. And we should say, when we're talking about AI there, we do mean generative AI specifically. So other forms of AI are not the same. Some forms of AI are, like some forms of reinforcement learning and that kind of thing, are much less of a problem than generative AI is. So that's essentially what we're talking about here. Okay, that matters because Well, it matters because carbon is a greenhouse gas, right? So the greenhouse gases, I'm sure you all know this, but the greenhouse gases are a family of gases, includes things like methane, nitrous oxide, and so forth. They sit in the atmosphere and they trap heat. And they're a bit of a mixed blessing. We do actually need them. If we didn't have any at all, temperature on planet Earth would be about minus 20 degrees centigrade. That's quite chilly. And as it turns out, too cold to sustain most life. So actually, they're quite a good thing, your greenhouse gases. The problem we have is since the Industrial Revolution, around about 1850, we've been burning a load of fossil fuels and doing various other things that have meant we've increased the concentration of greenhouse gases in the atmosphere. And fairly obviously, unless you're Donald Trump, but fairly obviously for most of us, if you increase the concentration of greenhouse gases in the atmosphere, you trap more heat. You know, I understood this at 7. It's not that hard. I mean, I couldn't explain the wavelengths of light and stuff at that point, but like, the fundamental principle is not terribly difficult. That's what this graph shows you. You've probably seen this graph before. This is the Bradley Mann hockey stick. The blue shaded area there is the margin for error. It starts in 1000, so the margin for error is quite wide at the beginning, and basically it narrows as we get close to the present day. It's a temperature anomaly graph. It bundles along doing, frankly, nothing very exciting until 1850, where it starts to climb. 1850 is the Industrial Revolution, right? And then it starts to climb quite fast. Now, I'm not sure how easy it is for you to see the vertical left-hand axis there, but it goes from minus 0.8 to plus 0.6. So what you're looking at on that graph is half a degree of warming. Half a degree of warming doesn't sound like a very big deal, and that's because it's not really. Half a degree of warming is fine. You've probably heard this sort of scientific consensus that we want to keep warming at 1.5 degrees. That's 1.5 degrees above pre-industrial levels by 2100. That's what that means. You probably know we're not going to do that, right? Or anything like it, actually. We're about 1.5 degrees now, more or less. We were just under, I think, 2 years ago, probably about the same last year. That doesn't actually mean that the 1.5 goal is gone, because obviously that's an average over time, because temperatures do fluctuate. But basically, we're there now, right? And we're not stopping. The best estimate I can find for where we will end up is about 2.7 degrees of warming, and that's not great. It's probably not species ending for humanity. Humans will probably survive, but not all humans will survive. Right? A lot of people will die, just so that we're clear. And there are some things that are quite unpredictable to do with food production and stuff that mean it's quite hard to know. So it's probably also worth saying that's staggering progress. When I was a teenager, which you can probably tell is a long time ago, but when I was a teenager in the 1980s, we were looking at 4 degrees of warming, maybe 5 degrees of warming, which is cataclysmic. So actually, to have gone from, let's say, 5 to 2.7 is pretty good. We've made real progress, which is, I think it's worth remembering, because I think it's very easy to get into a kind of doom loop when you start thinking about this stuff and thinking, well, this is terrible, but there's nothing very much I can do, and hopefully I'll be too drunk to notice or something. It'll be fine. I got so depressed as a teenager, I went off and read English literature at university instead of climate science. It was that bad, right? So this is real progress. It's good news. What's more, all of you in this room, assuming you're IT people for the most part, I'm not sure everyone is an IT person. I could see one person who isn't, at least. But those of you who are IT people, you can make a huge difference to this story. And I don't mean by becoming a vegan or flying less or driving an electric car or recycling. I mean, all of those are good things to do. I'm not knocking any of them. But that's not what I mean. What I mean is you can make a huge difference to this story by doing your jobs properly, by being good engineers. And the reason for that is, well, because IT is actually quite a significant contributor to this problem. So, how much carbon is IT responsible for? I'm going to nip back to the International Energy Agency. They reckon the global data center electricity consumption in 2022 was 240 to 340 terawatt hours. That's about 1 to 1.3% of all global electricity demand. What's interesting about that number, though, is that's just data centers. What it doesn't have in it is networks, which is a bit odd, really, because a data center you can't get stuff in and out of is pretty useless. If we add data centers in, well, we slightly more than double that figure. Right, so networks are another 260 to 360 terawatt hours in the same time period. That's about another 1 to 1.5% of global electricity use. I also stripped crypto mining out of there because I couldn't resist it. Crypto mining is 110 terawatt hours in 2022. It's about another 0.4% of all global electricity demand for what may possibly be the most useless thing we've ever worked out how to do with a computer. Those numbers are a little bit confusing, so let's pop them on a graph. Here is a graph. So IT there on the left is about 700 terawatt hours. That's about the same as Brazil. right? Brazil is 726 terawatt hours in the same time period. Brazil is not the largest consumer of electricity. That would be China, and then the US. It's about number 4, I think. But it's, like we are equivalent of a major nation state. We are vastly bigger than the UK, 316.9 terawatt hours in the same time period. So yeah, it's significant. And crypto is about the same as Norway, if you want a point of comparison for crypto. Also a nation state. So that's quite interesting. So as you can see, I hope, we're using a lot of electricity. And that matters because most of the electricity we're using, we don't make our own, obviously, so we get it by burning fossil fuels, we get it from the grid. The majority of electricity on the grids worldwide still comes from mostly coal and natural gas. The other thing we need to know before we get into the second half of the talk is the difference between embodied carbon and direct emissions. Most of what I've been talking up to now is direct emissions. So that's the electricity, or the carbon that we emit for powering a device or charging it, right? There is another form of emissions you need to be aware of, which is what's called embodied carbon. And embodied carbon is the carbon that's used in the manufacture, transportation, and eventual disposal of a piece of hardware. And that's actually quite significant. So for your end user devices, your laptops, your mobile phones, those kind of things, the embodied carbon absolutely dwarfs the carbon that we'll use to power it in its lifetime. That's an iPhone 13 mini. 84% roughly of all the carbon that will be responsible for happened before I bought it. About 84%. Right, so there's absolutely nothing I can do about that. And charging that on renewables isn't really going to make that much difference. I mean, it's still not a bad thing to do. It's not going to make that much difference. With your end user devices, your laptops, your mobile phones, what you want to do is hang on to them for as long as possible. 10 years is normally given as a good heuristic. That's a pretty reasonable indicative number. Quick show of hands, who's got a 10-year-old laptop or mobile phone? Ooh. Laptop, that's cool, right? Normally when I ask this question, there's like one bloke who puts his hand up, and I'm beginning to think it's like the same bloke, and he's following me around. It's nice to see a few more hands, particularly with a relatively small group. That's cool. Excellent. So yeah, so 10 years. If you're doing procurement for your companies, then buy from manufacturers that support the laptops and the mobile phones for a long time, the ones that are built better, and also then put pressure on your suppliers to keep supporting them for longer, so that they keep getting security patches and updates and what have you. Fine. For TPUs and GPUs and servers, it's not that simple. So TPUs and GPUs and servers also have a huge embodied carbon cost. However, they're also getting more efficient. And the particular way they're getting more efficient is they're generating less heat. That matters because in a data center, more than half of all the energy that you use is actually used to cool the hardware down. So the best PUE would be from Google, would be about 1.6. That means 60% of the energy is for cooling, roughly, and 40% is used to actually power the hardware. That, by the way, is why we tend to favor water-based cooling over air-based cooling as well. It's because water-based cooling is more energy efficient. On a global scale, using water to cool hardware is fine. Locally, it can be a problem. Like if you're operating a data center in a water-scarce area, then using the water to have LLMs make up nonsense is probably not a particularly good use of water, right? It's more of a problem locally, but globally it's actually fine and fine. The point here, though, is if you are running a data center with servers and things in it, I can't give you a heuristic, which is annoying. You have to go and get the embodied carbon cost from the manufacturer and do the sums. Sorry, it's annoying, but it's true. Of course, if you're renting them from Google, they're probably doing that for you, and you don't have to worry so much. Is that making sense? Fantastic. Good, right, so with that in mind, what I'm going to do now is I'm going to step us through a sort of typical AI project life cycle and think about all the places that we can save carbon as we go. Does that make sense? And that'll be the second half of the talk. So let's start with project planning. Good question to start is, do you really need to build this thing at all? This is the question IT people hate, because IT people like making things, right? That's what we do. So if someone comes and says, will you make me a thing? The answer is obviously yes, because that's what I like doing. We need to get away from that a bit. At the very least, it's worth asking the question, why are we solving this problem? Should we be solving this problem? And if we need to solve this problem at all, is inferencing the right way to solve it? Because it's going to be the most unpredictable and computationally expensive way to solve a given problem. So it might be it's also the only way to solve it, and the problem is worth solving. Fine, knock yourselves out, no problem with that. But if you could actually solve the same problem with a few if statements, maybe go for a few if statements. At least have a few if statements in reserve. Now, I've been in this industry 30-something years. I'm aware CV-driven development is a thing. right? Those of you who work in IT, you're going to have AI on your CVs, otherwise getting hired next time is going to be really hard, right? I get it. I'm also aware that FOMO is a thing that exists even for executives. I have been an executive. It's hard to believe, I know, but it is true. And I can tell you that I had it too, right? And your executive, fresh from the golf course, has probably burst into your office and is jumping up and down going, are we AI yet? Whatever the bloody hell that means. And suddenly you're supposed to be AIing all the things, right? That is a thing that happens. I'm sorry. But that doesn't mean you can't go, hang on, do we really need to be doing this? It's okay sometimes to push back. If you do need to do it, do you need to train a model from scratch? Training is still quite hard. It's not that hard, but it's quite hard, and it's very computationally expensive. So if you can get away with using a model that someone's already built, maybe using a bit of RAG to tune it for your particular use case, something like that, that's going to be a better option. Model choice also makes a difference, but here we have a problem. So I can tell you that Opt175B, which was Meta's equivalent more or less of GPT-3, used about 1/7 of the carbon footprint of GPT-3. I can't tell you that for any later versions of the models because I can't get the data, because OpenAI doesn't publish it anymore. Neither does Google, neither does Anthropic, neither does anybody. It is reasonable to assume that with each version of each new generation of the model, it's going to be probably several orders of magnitude worse than the last, but we just don't know because no one's telling us. Right? So the way I would think about that is use open source models if you can, because at least then you can benchmark what the model itself is doing, even if you don't know what it took to train it. Does that make sense? And only fall to proprietary models if you absolutely have to. There are a lot of very good open source models now on Hugging Face and places like that. A lot of the DeepSeek models and those kind of things are really excellent. They're totally safe, despite what America will tell you. It's just floating point. It's fine. So I would definitely favor open source if you can. Fine. The other thing to think about is, can you relax your service level agreement? Because if you can relax your service level agreement, then that will allow you potentially to run the workloads in greener locations. This is an energy transformation, right? So some regions are greener than other regions. The difficulty with this advice historically was actually it was really hard to know, because grids are actually weirdly complicated. And like the UK grid is connected to France's grid, for example, and we also have a load of consumer generation from solar panels on people's roofs and wind turbines that feed back into the grid and so on. It's actually quite a hard problem to go. You can't look at a bit of electricity and go, where did you come from and how were you made? It just doesn't work like that, right? Luckily for us, there's a company called Electricity Maps out in Copenhagen that's done all of this work for us. So all we need to do is go to electricitymaps.com and have a look. And it's even free, at least for the basic product, it's absolutely free. So just go and have a look. So there's the UK, for example. We're not too bad these days. I'm struggling to read the slide without my glasses, apologies. But yes, there's quite a lot of gas in there from what I remember, but there's also quite a lot of wind or solar or one of those. We're doing quite well. That said, if you're running workloads in Europe, I would favor the Nordic countries if you possibly can. Lots of hydro, lots of wind, very little anything else, pretty much 100% renewable, pretty much 100% of the time. So if you can, running somewhere like Sweden or Norway or Finland is a really good idea. Just doing that is going to make a massive difference, because our problem isn't using lots of electricity. Our problem is using lots of electricity that was made with fossil fuels. So if we're doing less of that, that's a really good thing. Making sense? Cool. The other thing to think about is one of the carbon-aware computing techniques, something called demand shaping. So the idea with demand shaping is you change how an application behaves, and you can do that a couple of different ways. You can have like a button, an option for the user that gives them some control, or you can sort of do it automatically in the background. That might sound like a weird idea, but if you've got a washing machine or a dishwasher, it probably has an eco button. And if you press the eco button, it takes longer but uses less electricity. Right, so in the case of your washing machine, it uses less water, it heats it to a lower temperature, it rotates the drums for longer, takes ages. At the end of it, you get clean clothes. Dishwasher soaks the dishes for, I don't know, 3 days or something, but eventually you get clean dishes popping out the other end, right? So you can do the same thing. If you're building an AI app, you could have a button on your website or whatever your front end is that says, do you want to watch the planet burn, or would you rather not do that? And give your customers some choice. Your marketing department might want different wording, but the principle is pretty good. It's a small crowd, I'll risk this story. I had a really fun conversation about a year ago with a prospect, so not a customer, but someone who reached out to me. And they said, we've launched a new version of our product, and it's not selling very well, and we're seeing quite high attrition, so we're losing quite a lot of customers. And we think it's because our marketing department are rubbish. Could you come in and tell us what we're doing wrong? So I said, sure, and went and had an initial meeting with them. And in that initial meeting, I said, what's the number one customer feedback or customer request or customer comment since you put the new version out there? And it was, and I quote, how do I turn this wretched AI stuff off? Actually, the language was a bit more colourful, but that was the principle. So I said, oh, that's interesting. How do you turn the AI stuff off? And the answer was, you can't. We spent a lot of money building it. We're certainly not going to let our customers turn it off. It's like, well, your problem isn't marketing then, is it? Let's be honest. Your problem is you've built the wrong thing. So demand shaping, I think, for AI stuff is actually a really good technique. Right? When you were thinking about whether you needed to solve this with inferencing, hopefully you were doing like proper problem solving and had several solutions. Maybe you could fall back to an alternative solution, either if that's what your user wanted, or alternatively at times when you're running on very carbon intense electricity. So you can use an API, watch time is one that you can use, WATT, electricity maps have one, the GSF have one. And with those APIs, you can basically do a prediction of when is the energy going to be greener. Find a time window and do the more computationally expensive thing in that window. Is that making sense? Cool. So that's demand shaping. Excellent. Let's move on to data collection. So here I am assuming that we've decided we're going to need to collect some data, either for a RAG database or maybe to train from scratch, one or the other. How much data do you actually need to collect? Now, if you're Sam Altman, the answer to that is obviously all of it. All of your data, every bit of intellectual property that humanity has ever created is mine now, I think you'll find. But for most of us, that's probably not actually what we need. Like most business applications, the vanishingly small number of successful large language-esque things I've seen in companies that actually work aren't large language models at all, they're small language models. Pretty much universally, right? They've trained them on a much smaller set of data than your Claudes or your OpenAIs or whatever. So have a think about how much data do you actually need. Also have a think about, do I need to collect any data at all? There's a lot that's just hanging around. Hugging Face, when I wrote this slide, had 300,000 data sets you could just download. Kaggle had 430,000. Maybe all the data you need is already there and freely available, and that means I don't have to collect it, which is great. And I bet those numbers are higher if you go and look now as well, because it's going up all the time. Another question is, does data collection need to happen on demand? If it doesn't, and it doesn't, because it's not latency sensitive, so there's absolutely no reason why it has to happen on demand at all, then you can use your what time or your electricity maps API and do the upload and ingestion and processing stuff on 100% renewable energy. There's no reason not to do that. I mean, there's your boss jumping up and down and going, oh yeah, that's a reason, but it's not a very good reason, right? So actually we could do a lot of this stuff on 100% green energy, and that would be a good thing. As it turns out, for any compute workload that isn't latency sensitive, demand shifting works out really well. So when we're thinking about training, I'm going to say to you, if you're training a large language model or any AI model, there is no reason at all why you can do that on 100% renewable energy. I mean, there is a reason, and the reason is it will probably take longer because you don't have it all the time. Right? That's the only reason, and that is, in fact, a problem for your marketing department. I'm going to wager that your marketing department could craft a pretty good message that says, yeah, we're working on a solution to this annoying customer problem. We think large language model might be the way to do it, but we're trying to do it in an ethical and environmentally friendly way. I'm going to guess that's going to land with a lot of customers. You know, probably not some customers, but a lot of customers, right? It's a marketing issue. If we did that, according to research from University College Dublin, we would cut our software emissions by between 45 and 99% during training. So it's quite significant. It's like, at the top end, it's all of it. Literally all of it. Right? So this is a thing that works. Now with demand shifting and data collection, you can't really do the follow the sun thing very easily because data has weight or gravity, depending on which metaphor you like. But basically moving data around is expensive and difficult. So you kind of have to be time-bound for a lot of this stuff. It's kind of true of training as well, but time-bound demand shifting is going to work out pretty well, pretty much all of the time. Cool. There are some other things in training that are really interesting. One of those things is federated learning. So federated learning is where we do on-device training. What we do is we have a foundation model that we hold centrally. We pick a cohort of devices. We send the foundation model out to the cohort. We do localized training on the cohort, and then we send the delta back. If we add some statistical noise into that process, like differential privacy, something like that, we get really strong privacy guarantees as a side effect, which is really nice. That's in fact where federated learning comes from. But it also turns out that federated learning works out quite well from an environmental perspective. The main reason is that you lose all of that cooling cost we mentioned earlier with our data centers, which is more than half, right? So this actually can work out quite well. There are some challenges with this because federated learning models will be slower to converge, right? It's a slower process, but it still works out quite well on the whole. Doesn't work for everything, but if it works for your use case, that's super cool. There is an extension of this which is using sort of nearer edge devices like smaller data centers. There's a company in Europe called T-Loop that are building data centers next to, for instance, municipal swimming pools, and then using the waste heat to heat water. Which is kind of cool. Build it near to houses, you can use it to heat houses. Now you can't do that with a huge data center because you don't want one of those next door, right? But you can do it with a smaller data center, and then if you chain some of those data centers together, you can still do large language model training on them if you've got the right setup, which is super interesting. I'm doing a bunch of research on this at the moment. I can't unfortunately give you proper maths on it yet because it's quite hard to research, but I do think it's very cool and interesting. So worth keeping in mind. As a rule of thumb, data centers basically are great big radiators that do some computing as a side effect. So if you can make use of that heat, that's a really cool thing to do. Nice. The other thing to keep in mind with large language models, the reason large language models are a problem is essentially because they're big. So if we could make them smaller, that would be a good thing. Right? And that's just compression. We've known how to do compression in IT forever. Compression in AI is still an area of active research, but there are some good techniques to know about. The three main ones I'm going to rattle through here are pruning, distillation, and quantization. There are some others, but these are the three I'm going to go through. I'm going to go through this incredibly quickly, but there are links to the slides at the end and links to papers and resources if you want more. So hang on, it won't be too bad. So let's start with distillation. The idea of distillation is you have a small model and a big model. You capture successful training runs, successful inferencing runs through the big model. You use those to fine-tune the smaller model until the smaller model is good enough for your use case, and then you send all the requests to the bulk of the requests to the smaller one. Simple, right? Yeah, mostly. There is a flaw in this plan, which is you have to know what a good inferencing run is and capture it. And that's actually quite hard. Because what does good mean to a large language model? How do you even know? It's not like it's empirical, you can't measure it, right? So like, what's good in a voice chatbot? I don't know. So it's quite hard. But it is getting easier. There are some tools around. Amazon has Bedrock, for example. A distilled model will be, they say, 500% faster and about 75% less expensive than an undistilled Bedrock model. You can reasonably assume that that's also 75% less carbon or thereabouts, because cost is a pretty good proxy most of the time. Right? It's not going to be perfect, but it's good enough for our purposes. There is an emergent category of, I'm going to call it AI middleware. I'm not sure that anyone else is calling it that, but it's a good name, so hopefully it'll get adopted. VMware Tansy, things like that. They have a lot of the blocks you need to do distillation. I'm not sure they're officially doing distillation, but it seems like a reasonable logical leap to assume that that's going to come. I think that's going to get quite mainstream quite fast. Quantization. What is a large language model? Well, it's a collection of 32-bit floating point numbers. That's it. That's all it is. If you step the precision of the floating point down, say from a 32-bit floating point to a 16-bit floating point, or even an 8-bit integer, or even, if your hardware allows it, a 4-bit integer or a 3-bit integer, well, it gets smaller, doesn't it? So that's cool. So there are ways that you can do that. You lose a little bit of accuracy along the way, but it generally works out quite well. Google has AQT for tensor operations in JAX. That's a GitHub project, so you can go and have a play with that if you're doing tensors and see how it works out for your particular use cases. It will work out quite well, but you do lose a bit of precision. Generally, though, it's kind of cool. I mentioned autism at the very beginning of the talk. My favorite autism or / neurodiversity theory is that it is a consequence of a thing called synaptic pruning not happening or not happening quite right in mammal brain development during the brain development process. It's a great theory. I went down a happy rabbit hole researching it and came to the conclusion that the research was a lot less compelling than the theory, which was annoying, but I like the theory a lot. It might be true. So in our brains, as we're developing, our brains, by some magical means, get rid of synapses that it decides it doesn't need. and I'm not being flip when I say it's magical means, we don't really know how this works, or at least I certainly don't. It's a bit peculiar, but it does work out. Could we do the same thing with AI? It would be great if we could. If you've ever interacted with an insurance company chatbot that's not properly guardrailed or something and thought, well, it clearly can't help me with my insurance, but maybe it can give me a cheesecake recipe or write some Python code or something, and it probably can if they haven't guardrailed it properly. That's kind of funny. It's not very useful. If we could get rid of the cheesecake recipes and the Pokemon characters and all of those kind of things, make the model a bit smaller, do a bit of pruning, that could be kind of cool. Again, there's quite a lot of it's harder than it sounds, because actually identifying what all the floating points actually do is quite tricky. But it's interesting research, and it is happening. Fine. All of those techniques can be done during training, and if you do them during training, you make the training run shorter. Fine. You can also do them at the end of training, which reduces your cost per inference. And that's sometimes easier. It's certainly easier to reason about. Now, again, here we have another data problem. Logically, it seems to me likely that running the thing in production afterwards probably uses more energy than training, eventually. But I can't prove that because no one will give me the wretched numbers. But I'm going to say I think that's quite likely. So even if you're not doing any of the pruning and quantization stuff during training, I would still argue it's worth doing at the end because it will reduce your cost per inference. Basically, it reduces your operating cost, which is cool. Yes?
Would that also reduce the emissions as well if you do
yes.
pruning and stuff like that?
Yeah, because if the model is smaller, then the cost per inference is lower.
Right.
That means it's using less energy. That means it's emitting less carbon.
Right.
Assuming you're running on non-renewable energy.
The training bit as well.
Yes, because again, you're reducing the length of the training run, so that the total energy you're using is going to be lower.
Okay.
Does that make sense?
Yes.
Cool, yeah, brilliant. Yes, so yes, it totally works. There's another really interesting technique that I wanted to mention here, just because I think it's the coolest thing, which is something called speculative decoding. The trouble with mentioning speculative decoding is I then have to try and explain it. It's really hard to explain. Okay, let's give this a go. So, first thing to understand is, when you put a prompt into a large language model, it responds one token at a time. Right? You can think of a token as being word or part of a word. Right? So it's completely serial. Yeah, you put a question in, and it comes back literally one word at a time in serial. Which is interesting, because TPUs are not serial bits of hardware, right? They can run a lot of stuff in parallel. It's just that responding to a large language prompt is not one of those things that parallelizes. So what that tells you is that our hardware is not processor bound, it's memory bound, which is interesting. The second thing that is interesting is that some words are really easy to predict, and other words are less easy to predict. So imagine for a moment you have a small language model and a large language model, and the small language model races away predicting all of the easy words, and the large language model comes along behind doing the slower words, or the harder words, right? You're now running some stuff in parallel. And it turns out that even if some of the predictions that the small model makes is wrong and you have to throw them away, it will still end up being quicker, which is nice. If that's sounding familiar to you, that's how branch prediction, pretty much, that's how branch prediction works in a modern CPU, right? It's kind of the same idea, just applied in a different way. What you're doing is you're increasing concurrency by calculating tokens in parallel. For your users, that's wonderful because it means they get a response quicker. Right, so you're not waiting as long for the wretched thing to come back to you with the wrong answer, which is great, possibly. And it also reduces the inference time. So that's really interesting. There are variations on this, like various mixture of methods, mixture of experts methods, where depending on the complexity of the query, you can kind of break it up and send the easy bits one way and the harder bits another way. There's a lot of really interesting stuff that's happening in this space. Beyond that, though, an AI workload is just a compute workload, which means it's like every other compute workload, which means all of the stuff we're already doing, I wish, all of the stuff we should already be doing, applies to AI like it applies to everything else. There are, in fact, only 4 things you need to know. I would say. There are 4 things you need to know about green IT. That's it. Take a photograph of this slide, you'll be experts. The first thing is use the smallest hardware configuration that can safely execute the job. As an industry, we use over-provisioning as a risk management strategy. We've done that for at least 30 years, certainly as long as I've been in the industry. The reason we do it is historical and weird. It's because procurement used to be incredibly slow. So if I was working on an app in the 1990s when I started, and we didn't have multi-tenancy, so every app had its own dedicated hardware. And at some point, someone from procurement would come along and say, how many servers do you need for your new app, Charles? So what I would do is I would get someone to write a load of load tests in probably LoadRunner or something equally ghastly, right? We'd work out the maximum possible number of simultaneous users on the system. We'd run that workload at full tilt. We'd look at the number that came out, and that would be, I don't know, 2 servers or something, and we'd go to procurement and go, 4, please. And no one ever asked us why 4, because we just did that, right? We still do this. I did an audit for a company about 2 years ago. 50% of all of their cloud infrastructure was totally unneeded. We just turned it off, nobody noticed. Halved their cloud bill before we did any work at all. Run an audit in your company and you'll be a hero. You'd be astonished how much is just pure waste. You can just get rid of. A lot of the wins are really easy. The second thing is run compute in areas where there is low carbon electricity in abundance. It's fairly obvious. And also where there are credible plans to make the grid even greener. Everyone is on a journey, right? So if you're going to pick a region where A, there's already lots of green energy available, but B, the government is actually serious about continuing to make that better, right? Don't run anything in EC1 in Amazon, because that's Virginia and that's coal and it's never going to get any better. Right, just don't. There's no reason to. Now, there are some subtleties here, right? Networks make this complicated. But data sovereignty also gets kind of interesting. There are situations, like I was out in Australia at the back end of last year, you're screwed. Right, the only place that's green for energy in Australia is Tanzania, and there aren't a lot of data centers in Tanzania. Sorry, tough. Nothing you can do. This doesn't work everywhere. Works really well in Europe, though. Yeah, there are complexities, and networking is another one, right? If you're sending a lot of traffic, we saw earlier that networks, like more than half of all the energy we use is actually in networking. So if you're sending stuff a long way, you've got a lot of latency, you're also incurring costs. But the general principle is pretty sound. Along with that, fairly obviously, use cloud services from cloud providers that have data centers in the regions in which you want to operate, obviously. Also, have tooling that you can actually use to optimize workloads. So right now, Google's tooling is actually pretty good. Certainly the best of the 3 big ones. You can do workload optimization with it. It's a little bit painful, but you can. You can also do workload optimization with Azure, Microsoft. It's a little bit more painful, but you can do it. It's slow, but it's doable. You can't do it with Amazon at all, not even slightly. Don't even try. All you can do with AWS is buy carbon credits. Now, AWS know that that's a problem. I know this because I wrote a very rude article about them about 3 years ago, and they didn't speak to me for about a year, and then they started speaking to me again, so I know they're doing work. And in fact, they've published a couple of updates in the last year. We've got Scope 3 for the first time, which is nice. We've also got, the methodology they're using is actually, there are some things about it that are unique and interesting that other providers don't do. If you want more detail on that, ask me afterwards when I'm not on camera. But there's some very interesting stuff that they're doing. So I think if you're already on Amazon, I wouldn't move away from Amazon. But if you have the luxury of being greenfield, pick Google or Microsoft as a starter. There are some companies like GreenPixie, for example, that can also help, particularly if you're multi-cloud. So that is another route to think about. And then beyond that, optimize the execution time of the jobs to further reduce your footprint. So that's the demand shifting, the demand shaping, the carbon aware footprint stuff. I think one of the things that's slightly unfortunate about green software in general is everyone got very hung up on demand shifting and shaping. And it's cool and interesting, but it's like the last tool in the toolbox, right? Most of you, I'm going to guess, unless you've done a lot of this already, can probably make a huge, huge difference to your carbon emissions by just doing the first 3 things. And only start reaching for things like demand shifting and shaping if you've got no other options. Likewise, don't do code level optimization. There's very little point. The chances are, right, like rewriting everything in Rust and C++. Will that be better? Yeah. Is it worthwhile? No. Most of the wins are in ops, pretty much across the board. Those of you that are software architects, I want you to take one thing away with you, and this is this. Sustainability ought to be a top-level concern, right? You've got a load of other top-level concerns. You've got cost and performance and security and regulatory concerns and reliability. Why is sustainability not one of those? It should be. There's no reason why it shouldn't be, right? So as an architect, I would really encourage you to think about putting sustainability into your architecture practice just as a standard concern, a standard thing that you think about. One of the things that's nice about that is it's actually quite subtle and interesting work. I've made it sound very simple, but there's actually a lot of really interesting trade-offs and subtleties in the detail, which make it really fun as architecture. It's definitely something you should be thinking about. I'm going to leave you with my favorite Kenyan quote. It's a proverb, and like a lot of proverbs, attribution is hard, but I'm going to say it's Kenyan. Treat the earth well. It was not given to you by your parents. It was loaned to you by your children. I like that a lot. If you want more reading, here are some books. The two on the left, embarrassingly, are my own, but they are free, so that's good. The Developer's Guide to Cloud Infrastructure Efficiency and Sustainability. I wrote that because people at conferences kept saying to me, like, what's the 101 guide to this? So I went, oh, I better write it then. You can literally read that book in the morning, and it will cover a lot of this material, not the AI bits, but it will cover a lot of the other material in a bit more detail. I've got Kubernetes at the Edge up there. That's also a free download. I've got it there mainly because it's talking about Edge stuff. And you saw in the context of federated learning, that's quite interesting. The Building Green Software book, the Ankari Sarah Bergman, Sarah Sue book, is kind of a definitive book on this subject. I hope you've all read it. If you haven't, rush out and read it immediately. And I've added Hannah Ritchie's book, Not the End of the World, there. I love that book. It is my favorite. If I'd read that as a teenager, I might have been a computer science nerd and not a climate nerd and not a English literature graduate. It's a really, really good book. And the follow-up, Clearing the Air, is very good as well, but that one, if you haven't read it, is well worth reading. I don't agree with everything that she says, but she's always interesting and well-sourced, and well worth reading and well worth listening to. If you want a copy of the slides, if you scan that QR code, that should take you to a page on my website, which is connaissance.com, which has the slide deck and all of the resources that I mentioned, if everything's working. So you can go and grab it from there. I've been Charles Humble. Thank you all very much for listening.
Amazing. Thank you, Charles.
Pleasure. Do we have any questions? We've got time for
Yeah,
questions.
I was just going to say, if anyone has questions, I'll run a mic over to you.
So I program, and part of the programming is I will use like an AI sparingly. But I've got I've got Olama running at home on my like Mac Mini. Versus like the VS Code inbuilt sort of AI models. I was wondering if there's like a rule of thumb if like say self-hosting is more sustainable, or if it's like really like it depends.
It's a real it depends.
Okay.
I'm actually going to say something that might be slightly controversial.
Sure.
I wouldn't worry too much about personal use of large language-based coding assistants in terms of your carbon footprint. Because actually, if you look at your total carbon footprint and think about the impact of having some of your code being written by a large language model, it's going to be pretty trivial. It's also super hard to measure. So one of the things about large language models which makes them really annoying is that there's like no meaningful way of averaging like cost per query, because it depends on the query. Like some queries are quite cheap, some are stupidly expensive. How do you know which? Well, you don't. Right? If you're running stuff on your own Mac Mini, quite an interesting thing to do would be to get a plug that measures the amount of electricity it's using. Measure that. You know, you could even build a little app. You could even vibe code it. You know, build a little app to like measure what it's doing. That sort of stuff. That's at least it's interesting, and at least you know. But quite honestly, as an industry, we're all going to have to adopt large language models for coding, whether we want to or not. It's never going to be cheaper than now because all of the companies are losing money, and that's clearly not going to work out long term. So I'm going to say I wouldn't not use them. I mean, if you've got like strong ethical objections, that's slightly different. But I would not use them on carbon awareness grounds, because if you think about your actual carbon footprint, it's not going to be that significant, chances are. The problem with AI is more one of scale, right? Individually is, but running it at scale is a huge problem.
That makes sense.
Does that make sense?
Yeah, I think it's more of a I want to do it myself objection. but
Oh,
yeah,
I think there are very strong reasons. I think running large language models locally is generally preferable. If you care even slightly about privacy, I mean, you should assume that everything you put into a large language model is public.
Yeah.
So if you're putting anything in that's in any way sensitive, that's a very bad plan. I do some work that I'm not allowed to talk about for a company I'm not allowed to talk about, but I would be fired immediately if I put anything into a large language model on that basis, right? And they're not wrong. So if privacy is a concern, yeah, run, DeepSeek or something on your laptop, absolutely the way to go, no question. Might be better environmentally, might not be, it's a bit hard to know. But yeah, overall I wouldn't worry too much.
Okay, thank you very much.
Cool. Any other questions? Yes.
Hey, so you mentioned open source models from like an ethical perspective in terms of IP. How important do you see open source models in terms of improving the green footprint of AI? Or an open source approach to AI?
Well, the one advantage that you have of an open source model is you can actually measure the damn thing. Right, so in the absence of, you can't measure what it costs to train, assuming it's pre-trained, but you can at least measure what it's doing afterwards. If you're using Gemini, you've got no way of doing that at the moment. Google's not going to give you that data, right? So from that point of view, it's better. I would definitely favor open source models where I could at this point. Sometimes, the frontier models are better at certain things. Like if you're doing something that's super, super cutting edge, you're probably only going to be able to do that with a Claude or a Gemini, chances are. But for an awful lot of things, I like being able to measure what's going on. I like it from a privacy standpoint. So for those reasons, I would favor it. But we are working in the absence of real data. So it's really hard to say. Like, I know Google is doing really good research on bringing the cost per inference down. The speculative decoding stuff, that's Google's work. They've talked about having brought the carbon cost of a Gemini query down by something like 33 times a year. So they are doing serious work. They will probably end up being better in the end because they've got infinite resources to all intents and purposes. And also because economically it's in their interest to do so. But I would still tend to favor open source models where I can. I think as a whole, open weights, open as much as we can is just better for what we're doing. Because there's a lot in here we don't understand. There's a lot of quite frightening things about the psychology of this and various other things. I just think it's better doing it out in the open, just instinctively.
Because I'm not any expert in AI, but to my perspective, it seems like all these companies are doing effectively the same things. If it's the same algorithm that was developed in the 70s, they're all just kind of computing.
Oh yes, absolutely. There's very little difference between a Claude and a ChatGPT and a Gemini, really and truly. So you can swap one for the other, and half the time you wouldn't really notice. They have slightly different personalities, but fundamentally they're not that different.
Yeah. Okay.
And actually, again, if you think about it in a Wardley mapping sense, I think we've basically moved to commodity already. I could be completely wrong. Don't take this as gospel. But I think Sam Altman's argument that we just make bigger and bigger models and they get better and better is not turning out to be true at all. There's actually not, as far as I can tell, been that much progress in well over a year now, which implies that that's not true to me. It doesn't mean we won't make progress, but I don't think we're going to make progress by scaling. I think we'll make progress in other ways, probably. I can't be 100% sure. But yeah, and another slight source of frustration is, yes, you're absolutely right, like Anthropic and OpenAI and XAI and all of these companies, they're basically all doing the same thing. Couldn't we just do it once?
Yeah, exactly.
It'd be nice if we could. Yeah. No is the answer, but it would be nice if we could.
Great. Thank you.
No problem. Any other questions?
Cam, have we got any online? Nothing online yet. Anyone else?
We've talked a lot about emissions, and I think you mentioned cooling and water.
I did, briefly.
Yeah. A lot of the operational savings in terms of emissions are super useful. What about water and kind of that acute usage in quite a quick way to cool systems?
It's a super hard question. So I think I said already in the talk, but the thing about water-based cooling is it's more energy efficient when compared to air-based cooling. So when you're thinking about it in purely carbon terms, generally water is going to work out better. That is starting to change. There's quite a lot of work going into ways that you can do air-based cooling that are more energy efficient, but it's still not as good as water. However, water is going to be, as we get hotter, water is going to become a scarcer resource. And I think that's one of those places where the industry kind of needs to wake up a bit and go, hang on, we are at the point that people are going to be waving pitchforks at us if we don't start getting a bit more sensible about this stuff. I think using water-based cooling in areas of water scarcity is pretty indefensible even now. I just don't, why would you do that? It doesn't make any sense to me at all. Yeah, not really. But globally, interestingly, if you look at the data from a global perspective, water-based cooling doesn't make a lot of difference to the total amount of water available to humans, but it does make can make quite a big difference locally. So it's a real it depends question. What I think is encouraging is there is a lot of work going into other methods of cooling hardware. And also hardware is just getting better. Like the Mac I've got there is a M4, I think. I've literally never got the fan in it to turn on. Not once. And I've tried. It's got one in there. I can get it to turn on by hacking the BIOS, but I haven't been able to get it on by doing actual workloads, right? So the amount of cooling that like ARM-based stuff needs is less. So again, if you're thinking about ways to run other workloads, non-AI workloads, ARM is going to work out better than Intel, as a rule of thumb. Or in fact, AMD will be better than Intel. Intel is terrible. Don't use Intel. I said that on camera. Naughty Charles. Tut. But yeah, so Intel is not great. AMD is better. ARM is better still, as a rule of thumb, in terms of cooling. It depends what you're doing, right? I mean, Intel is good for floating point math, but most of the time you're doing that on a GPU these days anyway, so who cares? Actually, AMD is pretty good for a lot of stuff these days. So yeah, I would, again, it does depend, obviously it depends what you're doing. But thinking about processor choice makes a difference at scale too, is I suppose what I'm saying.
I'll just follow on from that one. As a representative of the water industry.
Hello, water. God, that's brave, saying that in public.
I know. So, so data centres and water demand is just, it's really interesting conversation to be had. I'd say what Charlie was saying about globally, about whether it's an issue or not. Locally, completely agree. One of the challenges we've got in this country is that we're being asked to go with national growth plans and targets, but we don't actually have any numbers or information to work on to go, well, what would that demand be? How many data centers are we looking at? How much water is there? What kind of design are we looking at? Are we looking for closed loop systems, open loop systems? Where would they be put? And as we found last year, we did have a very prolonged dry weather period. We're going to have more droughts coming on in the future. And we are a dry part of the country. And that's one of the challenges I've got over the next year, is actually trying to guesstimate that to put in our next water plan. So any information you can give us in the future, Charlie?
I will keep it in mind. Again, it's genuinely difficult, right? Because the answer is we just don't know. Yeah. Right? A lot of these things are moving targets, and that's really hard if you're trying to do predictions. It's genuinely difficult. That's super interesting. I think there's a wider message for IT in general here, which is we just need to be a bit more open. In general, it's pretty indefensible that I can't know. If I'm an Anthropic customer, the fact that Anthropic is not legally required to tell me how much carbon I'm using is indefensible in my head. Like, why is that allowed? That makes no sense at all to me. And I do think regulation is going to end up being part of the answer here, by the way. I don't think it's going to be all of the answer, but I would love to see, for example, a carbon tax. Like every single economist I've ever asked about this has said we should have a carbon tax. It's actually the only thing economists agree on, as far as I know. But it is the one thing economists agree on. So I would love to see a bit more regulation in this area. But yeah, it's really hard. I'd love to be able to tell you, talk to me afterwards, I'll give you all the details. But I can't say that because I have no idea. Sorry. It's tough. It's really tough.
Any more questions? Yeah.
So some of the hosting providers will say that it's too difficult to measure the carbon outputs. What's your response to that sort of, so AWS has said in the past it's too difficult to measure. I know they're making improvements.
It is actually quite hard. It's quite a serious engineering effort to get realistic numbers for all kinds of reasons. I mean, a simple way to think about it is, if I've built a data center, I've got a load of workloads that are running. Some of those servers are idle, which means that I'm not sending any traffic to them, but they're still on, so they're still using energy. How do I proportion that out to my customers, right? Sounds easy, it's actually not that easy. Just as like one really trivial example, if you've got like a noisy neighbor in a server, so somebody is using disproportionately more energy than somebody else, you've got to be able to divvy that up in some meaningful way. There's a lot of genuinely quite difficult engineering in here. On the other hand, Google seems to be able to manage pretty well. Microsoft seems to be able to manage pretty well. I think AWS probably thought that they could get away with it, and they were right. They got away with it for a long time. They're still the biggest cloud provider in the West. So I would say the one thing that is true about Amazon is still true about Amazon is they do actually care what their customers tell them. So if you're on Amazon, beat up your customer service rep. I mean, not literally, but go and talk to them and say that this matters. Why are you not doing better? If you don't do better, I will go to Google, because Google is better. And that will make a difference. They do listen to their customers. As I say, it's not easy. They do have a proper team. The person who's leading that team now is pretty good. The methodology that they've documented is pretty solid. In fact, I think it's the best of the three. But it doesn't give you the precision you need. Hopefully that will come. I hope it will come in the next year or so. But as I say, in their defense, it's not trivial to do. It's certainly not trivial to do at scale, but neither is it impossible. And I kind of think we're a bit past the making excuses stage. It's like, there are really hard problems with greenhouse gases, like food, right? The entire farming industry is essentially fossil fuels, right? That's a really difficult problem to solve. The human population is still growing. It will peak at some point, but it's still growing at the moment. Farmers need to be able to produce more food using less fossil fuels while the climate is making that hard. That's really tricky, right? Using green energy for your cloud data center, not that difficult. Right, let's get it together. and that way it buys us more time to solve the really difficult problems, like how on earth do we feed people without nitrous oxide or methane, right, which is a lot more difficult.
We're going to end on that very deep note, or any more questions? Right. I think we're good. All right. Thank you very much, Charles. That was awesome. Hope everyone learned a bit and can take that away back to your desks tomorrow and try and apply it. So yeah, as we mentioned, April event, third Wednesday of April, Adam Newman's going to come and talk about web sustainability. For anyone in the room, we're going to go to the pub after this, so stick around if you want to have a drink and a chat about what Charles spoke about. I think you might have to run off, is that right? Or are you? Okay, great, yes. Charles will come and you can chat to him about all that cool stuff. Yeah, thanks everyone for coming. See you next time.